Okay, hey everybody. So we're just about to start a new chapter, chapter 4, and um, chapter 4 is called Applications of Differentiation. So we've been learning, the definitions of what is a derivative, and then several rules for how to find derivatives. And so now we're going to focus on what you can do with it. And the first thing you can do, which is a really important thing, is finding the maximum and minimum of a function. So you can imagine in many practical situations, uh, we want to find the best or the worst or the fastest or the slowest, the cheapest, the most expensive, right? So um, those are all examples of finding maximum and minimum values. So um, now you can already do this for some functions. So for example, a parabola here. What is the maximum value of this parabolic function? And if we have the graph, well, we can look at it and we can see it looks like the maximum value is here. And it looks like the highest point is, that would be 16, right? So that occurs at the point 2 comma 16. So that would mean that the maximum value is 16. Now, how would we do this with calculus? At the peak, so at this highest point, the tangent line is flat. That's the key idea. So at the very top, the tangent line is flat. Everywhere else, it's not flat, right? So the one point that's the highest is the one point where the derivative is 0. So we can find the peak if we let the derivative equal 0. So what is the derivative of f prime? Of f. Derivative of 12 is 0. Derivative of 4x is 4. Minus 2x equals 0. So that's saying that the slope of the tangent line is 0. And then if we solve that, we're going to get x equals 2. And then y is the f of 2, which is 12 plus 4 times 2 minus 2 squared, which is 16. So that means that the maximum value of f of x is 16. So we're going to be doing this kind of calculation throughout this section of this section. There are a few more complications, but this is the basic idea. To find the maximum, we look for the places where the slope is 0. The minimum is also a place where the slope is 0. So some definitions here. Right. Let c be a number in the domain of the function. So c is an x value. That's an x value. And f of c is the absolute maximum if f of c is greater than or equal to f of x for any x, for all x in the domain. So I write it like this: x belonging to D. That's the domain. Absolute maximum means it's the very highest point. There's no other point higher than that. F of c is the absolute minimum if, same thing, just the other way around, f of c is less than or equal to f of x for all x in the domain. And so if we look at this picture, there's an absolute minimum here that looks like it's at the absolute minimum would be f of 6, which is minus 4, it looks like. So we'd say minus 4 is the absolute minimum. It's the smallest, it's the lowest point in the whole graph. Now, if you look at this graph, it actually has no, this goes on forever here. This is an asymptote, it looks like. So this graph actually has no absolute max. Because any specific point is still lower than some other point, right? If I pick any specific point, I could go higher just by going a little bit more to the left. Okay, now there's another kind of maximum called a local maximum. F of C is a local maximum if it's greater than everything near it. If f of C is greater than or equal to f of x for all x that are near, and I'll have to explain what that means, near C. So here's an example of the local max. If I say I pick this interval from, let's say 2.5 up to 3.5. That's not a very accurate sketch then, is it? So from 2.5 up to 3.5, that is the highest point for any x in that interval. So near means in some open interval around C. It means in some open interval. Around C. Now, we can't be very specific there because the interval might be very narrow or it might be wide. As long as there's some interval where that C gives you a maximum for that interval, then it's called a local max. So for example, what if I had a graph that looks like this, right? Then all of these are local max. All of these little tiny bumps, these are all local maxima, we call them, because they're the highest point in some interval, even though they're not the highest overall. Okay, so that's a bit of a tricky concept. F of C is a local minimum if f of C is less than f of x for all x near C, i.e. in some open interval. Let me write it down here. i.e. for all x in some interval AB containing C. And it has to be an open interval. That's really important. This is open, meaning not including the endpoints. So a key thing is that C can't be the end of the interval, not including endpoints. I'll say it again. C is not allowed to be at the end of the interval. So for example, this one, that's not a local min because there's no open interval containing it. Because it's already at the endpoint. Okay, so I hope you caught the difference between absolute and local here. Okay, so we're going to apply these concepts now to a more slightly more complicated function. Okay, so this is example number 49 from the textbook. Find the absolute max and min values of this function on the interval -2 to 3. Now, after we make some progress here, we're going to actually sketch the graph based on Desmos, but for the moment, we're going to try to do what we can without the graph. So what we're looking for is somewhere on this interval from -2 to 3, the graph looks like who knows what it is, right? And we're going to try to find the absolute max and the absolute min, whatever they are. But we don't know what the graph looks like yet, right? So where do we look? There's two places that we look. Actually, there's three. We look for places where the derivative is 0. Those are possible. If we don't have the graph, we don't know whether the bump is higher or lower, but we know that it could be at a bump. It could be at any of those bumps. So we're going to look at places where f prime of x is 0, and also we also have to check the endpoints. The endpoints might be where the maximum is. For example, let me just extend, if I extend this just a little more, that endpoint is now the lowest point, right? So that could be the absolute min at the very left side, right? Okay, so that's the strategy. So let's take the derivative. So first, let's call that 1 and 2. So first, we're going to find f prime of x. And let me just write f of x again here. So f of x is 2x cubed minus 3x squared minus 12x plus 1. So the derivative, now fortunately, when I differentiate, it's going to become an x squared function here. So that's 6x squared minus 6x minus 12. So I'm going to let that equal 0. And then I'll find the places where the tangent is flat. So let's see, I can actually factor out a 6 here. And I can divide by 6. So let's see, can I factor this? X minus 2, x plus 1, that will do it. So there are 2 places. So those are 2 places where the tangent is flat, or horizontal tangent. So those are what we would say they're candidates. They're candidates for places where there might be an absolute max or min. So we're also going to check the endpoints. Okay, so first what we do, before I need to actually find what is the value of the function at those points. So what is f of 2? I have to actually put it into the function. And what do I get? So that's 8, 16 minus 12 minus 24 plus 1 minus 20 minus 19, right? What about f of minus 1? To be careful with the minus signs here. And so what is that? That would be negative 2, negative 3, plus 12, plus 1. So that's 8, right? And now we have to check the endpoints. So the left side is negative 2, right? That's the left and the right endpoints. F of minus 2 is let's see, so that gives me negative 8, negative 16, 4, negative 12, plus 24, plus 1, and that is negative 28, negative 4, plus 1, negative 3, right? Okay, and then f of 3. And so in the previous one, this previous point is neither the absolute max or the absolute min, because these ones up here are more extreme still. Okay. Minus 3 squared minus 12 times 3 plus 1. So here I get 27 times 2 is 54. 9 minus 27 minus 36 plus 1. Okay, so what is that? So that would be negative 27, negative 63, negative 62. Is that right? I'm a little worried. That seems so very large. Okay, so what we see is that the absolute minimum is going to be the lowest of all of these. It's the minimum of all these numbers, of all four candidates. So that would be this one, this one, this one, and this one. So I'm going to double check that in a second, but it's looks like it's negative 62. The absolute max is the maximum of all four candidates, which is 8. So let's have a quick look at Desmos, make sure we have the right, double check what we've done. Oh, they've changed the website a little bit. Okay. So what was the function? So it was 2x cubed minus 3x squared. And then what? It was minus 12x plus 1. And if we want to be very clever here, we can use these square brackets to tell Desmos, these braces, I mean, to tell it which interval to restrict it to. So just between minus 2 and plus 3. And so we're just looking at the that interval. So I can see the two places with the horizontal tangent, right? Let me actually make a graph that I can copy into my my notes. Okay, that's pretty good. And I'm going to take a little screenshot here. Okay, so we're going to paste that. It's a little bit large. Okay, so I can see that we got just about everything correct here. So at 2 and minus 1, we have horizontal tangents, right? So those were the points here, minus 1 comma 8. That was this guy, and then 2 comma negative 19 was this other flat tangent. Now my endpoints, looks like I haven't quite got it right. What happened there? Let's see. So at negative 2, what happens? That one's right. Minus 2 comma negative 3. But this guy, something's not quite right. That should be 3 comma negative 8, right? So let's double check that. Okay, so I have 2 times 3 cubed minus 3 times 3 squared minus 36. Okay, I think I see what happened. So this should be 27 minus 36, which is 9, minus 9 plus 1 minus 8. There we go. Okay, so now what? Now the absolute minimum is, now the absolute maximum is the absolute minimum is negative 19. There we go. That's the absolute min. Okay, so it's really helpful to make a sketch and make sure you've done your arithmetic right. Everybody makes mistakes sometimes. And that's the absolute max. Okay, so the how do we find the absolute max and the absolute min? We look for places where the derivative is 0, and we check the endpoints. There's a third place which didn't matter in this case. There's a third place to check, which is anywhere that the derivative does not exist. We'll talk about that more in the next video.